Hi, everybody. Evan again. I'm here for the second part of our dynamic distillation column. Remember our first column was on the whiteboard where we did our derivation of our dynamic distillation column, where we had a weir system in for each stage, where we basically had a hold up coming from the top of the condenser coming down to our weir, where the liquid built up until it got to a certain height, where then it overflowed into the next stage and then kept going down the distillation column. Um, we put all of our equations that we have for our condenser, our different stages, and our reboiler into Python. Okay. So let's first read the prompt is for part B. So a column has a total condenser, two equilibrium trace stages between the condenser and the feed stage, which we have represented here. This is like a representation where our distillation column looks like here, but I'll read the rest out. Of the feed stage and three equilibrium trace stages between the feed and the reboiler. The feed flows in at F equal to 1.5 moles per second with a mole fraction of 0.4 of the more volatile component. The relative volatility is assumed constant at 2. Liquid flow via overflow at a rate of 1.0 at 1.0 times our hold up minus our initial hold up, and then to the 3 halves, which is our Francis-Weir equation, where our initial hold up is 0.5 for all stages and 1 for the reboiler. The trays and the reboiler are filled throughout initially with the feed liquid at a hold up of 5% greater than the initial hold up. The initial condenser hold up is set to provide a flow half of the feed at a reflux ratio of 2. That's maintained at the distillate flow. As the distillate flow is ramped from 0 to half the distillate flow from 50 to 100 seconds in the simulation. And then we are supposed to simulate our time response over our first 300 seconds. Okay. So I know it was a lot, but let me break down the initial values that we have. Before we start, what we'll be using is pretty simple. Is this import numpy as an MP. We're using SciPy integrate for our solver, and then we are just using Plotly subplots to make subplots. Okay. Excuse me. Okay. So like I just mentioned, in here we know that we have our condenser saying the prompt, then we have in between our condensers for our rectifying stage, we have 2 equilibrium trace stages, and then before we hit to our feed stage. And once we hit our feed stage, we have 3 equilibrium stages in our stripping phase before we hit our reboiler. Okay. So in total, number of stages. So for NR, so number of rectifying stages, we have 3, including our feed stage. So 1, we have including our condenser, so we have 0, 1, 2. And then for stripping, we have 4. So that'd be from 4 to 7. So 1, 2, 3, 4. Okay. Oh, actually, I'm sorry. For rectifying stage, it's from 1 to 3. So it's 1, 2, and 3. We don't consider the condenser part of rectifying stage. So yeah. Then we know that our feed flow rate is 1.5 moles. We know that our mole fraction for our mole composition, our mole flow rate for our feed is 0.4. We know that it's all liquid coming in. So like I said, liquid flows. Not liquid flow. Where does it say that at? Yeah, just say liquid flow. So we know that our quality of our liquid flowing into the stream is 1 because it's all liquid stream coming into our distillation column. And then we also get stated that we have we have a reflux of 2. Right here, our reflux ratio is of 2. Initially, we do know that over time, it is only 2 from 50 to 100 seconds in the simulation, and then past 100 seconds, we do see it fluctuate throughout our distillation column all the way until we get to 300 seconds. So we will incorporate that later on in our Python. For our distillate, we know that it's half. And it's stated right here. Our initial condenser hold up is said to provide flow rate of the feed at reflux ratio 2 that's maintained the distillate flow rate is ramped from 0 to half the distillate flow. So we know our distillate is equal to our feed flow rate divided by 2. Yeah. And then we know that our relative volatility is assumed to be constant at 2. So we have that here. For our weir, we know that our weir is 1 because it states in our equation for our weir that it is 1.0, and then times our hold up and minus our initial hold up. So we already are given, it says it, but trying to be um not trying to say it, but says it. So our weir is 1. And then how we got our units, and I have it shown here. Um, so for our weir, we know that our minimum when we did our liquid minimum flow rate for I don't think I say this, but our liquid minimum flow rate, if we try to calculate it, it would be our weir times moles, uh our moles coming in minus our initial mole hold up, and then to the three halves for the exponent. So we put that in units. We know it's moles per second is equal to our weir, and then times our moles because it's just moles, and then to the three halves. We do algebra to get to the weir by itself, and we get that our weir is equal to, for units, 1/seconds of moles to the divided by half. Okay, so we can say our moles is right here. And then back to our prompt. For the stages, we know that our stage holdup is just 0.5 for all the stages. We know that our feed holdup will also be 0.5 because it counts for our stages. And then we know that our condenser and our reboiler start up as 1. Okay. Now our condenser would be, and it's not necessarily 1. We're using 1 for now, but this will change. We know that our condenser needs to be relative to our reflux, kind of equivalent to what our reflux is, real close to 2. So we will change that later on. And then our reboil, we know that needs to be a gain of 5%, but we will get to that later. We would start by this set up an equation for our holdups in general. So for our mole holdups, we just set an equation right now. So M holdup, and this will be equal to, we'll put this into a array. So in p dot r, and then we start off with, we know that we start with the condenser, so we start with the top. So we just start with the condenser. So condenser holdup, and then we need to get our stages of our holdup. So this will be, we'll do NP dot full. So we can fluctuate our shape. So we know our shape wants to be our NR. So for our rectifying stage of NR. Okay. And this would be -1 to get rid of the feed stage because we have our separate holdup for our feed stage. So it'll be NR -1. Okay. And then for our fill value, we'll just put in our stage hold up. Okay. So that would be our rectifying section. And then next we will do our feed stage. So feed stage. And then we will do the same thing for our rectifying section. So NP dot full of, I spoken this wrong. I was wondering why it was yellow. Okay. NP dot full, and then we do NS for shipping. -1 again to get rid of the reboiler because we already have reboiler for one of our holdups. And then fill it with stage holdup. And then let me shift enter this so I don't keep going all the way out over. And then lastly, we will just do our reboiler. Okay. So this works now. Now we have recording for our moles, flow rates for our hold up. So now next we want to do is set up get all of our initials out the way. So we will set up our initial moles because we know from our prompt that the distillation columns are already initially filled. So yeah, the trays and the reboiler are filled throughout initially. So we need to represent that as well. So initial stage values at t is equal to 0. Okay. So we know our initial moles. We can say this is equal just to our M hold up. and times 1.05. And this will be representing our currently right now, we're representing our reboiler because we know that our hold up is 5% greater than our reboiler, initial reboiler hold up, than our hold up. So we need to represent that. So our M hold up times 1.05. And then we also need to represent this in our condenser because like I said earlier, our condenser is close to equivalent to our reflux ratio because we know that our since it's a perfect controller, we know that we starts as reflux. It starts with the reflux ratio for the condenser before liquid starts coming down. Okay. So M0 at 0 is equal to, how can we say this? It would be, so what we would do is R plus 1, I have to remember the equation, divided by W, plus condenser. I'm pretty sure this is right. And I'll explain this as I remember this real quick. Okay, and I think we just have to bracket this off. Okay. So basically what this is, so we do a mass balance of the condenser for our reflux ratio. So we know our reflux ratio is our initial liquid is equal to our reflux times our plus our distillate. We plug that into we have two L initials. We have our L0 coming from our condenser. Then we also have an L0, what is it at? As the liquid coming out of our stage, of the condenser stage. So we have the L0 initially coming out of the dish of the condenser when it splits into the distillate into the flow, and then we have the actual L0 coming out the flow. So we have kind of two. So what we do, because we have a reflux and we have the actual stage mass balance, so we plug in the reflux balance equations of the L0 is equal to R plus D into the stage condenser mass balance for our vapor is equal to our liquid plus our distillate because we know it's perfect controller. Wish I could write this down. I try to put this on here but I accidentally forgot. But yeah, so hopefully this will help more. But yeah, we plug that in and then we use our Francis Weir equation. Because we know this our L minimum, we can set that equal to for our condenser stage. So we have our Weir times our moles minus our hold up to 3/2. So we can set that equal to each other. And then again, we are trying to, just have our M initial. So our, what is it? We're just trying to find the initial moles. So we're just trying to get moles by itself. So by doing this, we do some algebra, get moles by itself, mole flow rate by itself, and then we are able to get this equation right here. Okay. I know if I wrote it down, it may make a lot more sense. Sorry, I forgot to put it in my initial pages, so I couldn't add it to right now. Okay, so next, and then we would just do our x1s, because we also need our mole fractions as well. So our x naughts is equal to, and I'm pretty sure it's NP zeros. Yeah, NP zeros. And then and then this would be respect to MO. So our with respect to our flow, our moles, there's our initial moles, and then our compositions for our feed. Okay. Yeah, I'm pretty sure that's it. And then we can actually represent. I can show you this right now, so we see that we have it correct. Shift enter. Cannot interpret 0.4 as a data type. Okay. It said all string D types. So is it where? Let me try where. I think it's either zeros or where. 'Cause I know when I was doing this earlier, I kept getting the zeros and wheres mixed up. Yeah, it's zeros. It's definitely zeros. Hmm. Um, Interesting. Let me check real quick and I'll be right back. Yeah, small mistake. I meant to put MP4 like, because we're just reshaping. So we're using the shape of our most of the length of our rows that we have for our mole flow rate, and then we're shaping for our compositions instead of our flow rates. Um, this is a small mistake. Let's try this now. It should work now. Yep. So we should have eight values. Because we know we start at 0 to 7. So 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Yes, so we have that. We have our initial our whole fraction should be the same. It's coming out. So yeah, 0.4. And then we have our change in flow rates. We know that you see here our reboiler says 1.5 and 3.2. And that's kind of high. Um, hmm, that is kind of high. I mean, interesting. Interesting. Maybe it's right. We'll see later. We'll work it out later. It should be fine. If not, we will see later in the graph. Or I may just catch it if I probably make a mistake. I'll just recheck it later. But this is correct for now. We will go back to it later. If it's a problem. But now let's get into the rest of our initial stuff. I want to at least get through all of our initial conditions before we start actually doing our derivations for our condensers, all the stages, and our reboiler. So next we have our ramp system. Um, as you know, our simulation ramps up from 50 to 100 seconds in our distillation column. So we need to simulate that as well. So we need to have a function for this. And this would be a really quick couple lines. So to define a ramp, we have the respect to time, like I just said, and then we have a starting point, and then we have an endpoint. So that we represent as A and B. So for this, uh, we have two if statements. The first if statement, if if T is less than A. So if our time is less than our initial starting point where we want to start ramping, our ramp is 0. There's no ramp has that started yet. And then our second one is if our temperature is greater, if our time is greater than our end ramp point. So if we reach our end time variant for our ramp, we want the ramp at the stop. So when our time is greater than our endpoint for our ramp, we want the function to return 0. Turn 1. Okay. And then in between, we want our function to be t minus a divided by b minus a. Okay. So basically, we're saying that they're over time. Initially, whether we have no ramps, it'll be 0. Once we get to our threshold of when we have our temperature, our time enter in between our our starting time variant, we will go through this function here. So right now, if it was below a, it would just be 0 divided by 1, because it's 1 minus 0. So we know that has to be 0, but once we have our time function be above our threshold, over time, as our time increases, our ramp will keep ramping up until we have a function equal to 1, and then we have 1 divided by 1 is just 1. So our ramp function will end there. And then we can also plot this out too. So do fig is equal to make subplots. And then we'll do we have the t plot, and then we'll just do NP length space from 0, and then we just do 100 for our time. And then we just do what also 100 points short for each time. For our y plot, this will be equal to for our ramp. So for this, we'll do a kind of a mini for loop inside. So we'll do 2 times our ramp, depending on our time, and then we'll just simulate the 50 to, we'll do, 30 to 70. Well, we'll do 30 to 60 and small. And then um that'd be T plot. It'd be T plot. Yeah. And then no, it'd be T. Yeah, I forgot to put the for loop. For T and T plot. So basically what I'm saying here is that right now we are just what I'm doing is that I am multiplying my temperatures by my time by 2. So I'm doing that, I'm just having a for loop for so we can show the difference for our ramp. So all of our temperatures for our ramp will be multiplied by 2 in this scenario. And then like it will just keep repeating in the loop for the temperature that we have for T plot. Okay. And then let's put this out. So fig dot add scatter x plot x equal to x plot, T plot, y is equal to y plot. Okay. And then I'll do a layout because I don't want to get blinded. Because it is like my eyes will hurt. Fig updates layout. Okay. And then we just do a template. So you go to poly dark. And this should work. Oh, why is it not working? Hmm. Invalid value for the type of bulletin generation received for Y. Let me just skip that up. Fig dot add scatter. What's wrong with the Y plot? It's just not, can we not use that? What's wrong with it? It should be on. If Y properties is an array may specify as a tuple, list NumPy array as panda series. So this is a tuple. No, where are we getting that from? Let me check this. Be right back. Small mistake again. This has to be in list. Makes sense. Yeah, it has to be in a list. I mean, yeah, like it says here, as a list. Yeah, it needs to be like, yeah, an array. So now we see, starts here, starts at 0. We didn't get the rest of it. Then we hit to our 30, or our 30 is where we start our ramping up. It starts ramping up at 30, and we keep going all the way till we get to 60. It's about 60, 60.6. But yeah, we're ramping up all the way till we get to 60, and then when we get 60, it's above our threshold, and then we just cancel out to all the way to 1. Right now it says 2 because we multiply by 2, but yeah. Yeah. That's the basis of it, and then we can just like fluctuate around. So we want to do 75, we can do 75. We can play around with it, making it a longer ramp, making it a short ramp. We just do all the way to 40, short, quick ramp. See. So yeah. But yeah, oh, my bad. Misclick. Also while I was there, I also checked our initial stage values because I knew something was off. And yeah, our condenser is off because this is way higher than 2, so I knew something was off. What I forgot to add was the 3/2, the exponent 3/2 to this, and that's play a big role later, so we need to add that as well. So what we need to do is I will do this real quick. I'm just adding the 3/2. I just want to space this out as well. Okay. So now we should be good. That's not. Don't want that. Let me see. Why is it 4 now? Should be 4. One should work out. It should be around like 2.3. It's supposed to be 2/2. Let me see. Pretty sure it's supposed to be 3/2. Oh yeah, perfect. Never mind. Here it is. Yeah, it's supposed to be 2/3 because you divide the 3/2 when you do your algebra. Makes sense. This is why I write this out. Helps you out later on. But yeah, okay. Um, yeah. Here is the correct value for our initial condenser. So now we have our we have our initial stuff, we have our initial values, we have our ramp. And now we will start our defining our system for our column. All right, so to start our derivations, we will need to first find our functions. We'll just find our right-hand side. Let's go down. Find our right-hand side, and our right side will be respect to time, and then our vectors. So yeah, our vector. For our vector, we will have, what the heck? I don't know what that is. That's not even right either. I be hating this sometimes. Because they be giving me the wrong values and like things I don't ask for. Okay, so we know for our vector we need to split it up in two because we have our moles and we have our mole fractions. So for our moles, we need to actually state that. So we m, and then we have our mole fraction. So what we'll do is we just split our vector into two. So we do np dot split. Sorry, I just forgot how to spell. My bad. And then we just do our vector and then the split into two. So now we have our moles and we have our mole fractions for our liquid composition, and then we need also our mole fractions for our paper composition. So what we would do to find y, we actually um I did this earlier for us, but we will use relative volatility. So I remember stating, if you remember in our first video, I say this in the beginning for our initial conditions. But we need to use relative volatility. And I mentioned it in our prompt today, but we'll use relative volatility to calculate our y for this. So what we'll do, we have our alpha. We know alpha is equal to k1 divided by k2. We know that k1 is equal to y1 divided by x1, our vapor mole fraction divided by our liquid mole fraction. And then respect to one, whatever to one, species one. And then our K2 is just our Y2 divided by X2. And then we can equal out actually Y2 and X2 equal to 1 minus Y1 and 1 minus X1 to get similar terms. Once we have similar terms, we can then do algebra to get Y1 by itself. So we'll multiply denominators on both sides. Then we'll do some algebra. And then from there, as you see, we get that y1 is equal to our alpha times x divided by 1 minus our x plus our alpha times x. Okay. So we can actually put that here in our Python code. So alpha times x, which we know x is what we're finding from our function. Divided by, and I'll put this into divided by 1 minus x plus alpha times x. Okay. All right. What the? What did I say? I mean, Eds be doing stuff sometimes. Like, I didn't even ask for that. Didn't even ask for that. Bro, what is stop? Oh my gosh, I'm about to have an aneurysm. Okay. Good for Gucci. Thank goodness. Thank goodness. Okay. Sorry. Almost got into forward. Anyways, next we want to what is define our we can define our reflux now. Yeah, let's do a reflux. So as remember I said earlier as well, it says here as well, but our reflux, we know that initially is at 2, but it does not stay at 2. It actually changes over time. Um, it says here initial condenser hold up is set to provide a high flow rate, a feeder reflux ratio of 2 that is maintained as the distillate flow rate is ramped up from 0 to a half distillate from 50 to 100 seconds in assimilation. So that is basically telling us, so our reflux is basically is constant until we start ramping up. And then once we start ramping up, our reflux, it initially change it alternately just changes over time into our function to keep us so it can be steady state at the end. So what that means is that we need to supply a function for our reflux. So so we can see our reflux change over time to help with our distillation column. So what we need to do, we have to restate R. We need to restate our reflux. So we have to rechange what we have in here for initial. So restate it. And then we would actually need to incorporate this into our function. So we can do R divide our function as a reflux function. Um, and then we respect that to time because that's what its base is off. And then we'll also do our distillate because, like I said earlier, our distillate changes, our condensate changes as well once our ramp is incorporated. So we need to do our ramp from 50 seconds to 100 seconds. And then we multiply that by our feed and then divide it by half because we know it's half a distillate flow. So divide by our feed. And we know that our feed will be the reason why our chances are ramp because that'll be the vapor coming in. So and divide it by half. And yeah, that's the set value conditions for our distillation column. Yeah, now let's start our derivation. So now we need to state out our dependent variables in our distillation column. So we need to state out our change in mole flow rate and our change in mole fractions. So our DM and our DMX. I'll get back to this page. So our DM and then our DMX. So um uh, dependent variables here. So DMX, DM, and DMX will actually be the same. It's kind of nice. We know at first, there will be no change because nothing has happened. So what we can actually say, we'll just do MP0 and we'll do like and then like our M. So we have a shape for what our uh again for what our function, our change and our moles would be like for shape wise for our vector. And then we can actually just copy paste this A as well. Perfect. So now we have our two dependent variables. Next, what we want to do is we need our liquid and our vapor mole flow rates. So here are mole flow rates. Okay. We need liquid. Um, we need liquid and we need vapor. Um, liquid. Let's see. For our liquid, we know our liquid is based on our condenser. Um, so we know our liquid is just equal to our reflux plus our distillate. Well, that's no, that's for our condenser. What will liquid be? I'm having a brain fart. I'm having a brain fart. Well, enough for my vapor. Our vapor, because we have no vapor initially coming in. Our vapor would just be our vapor would just be MP zeros because there's no vapors in uh and the distillation column to start off with, but then it will change over time. So we just having set placeholders for now. And then for our liquid, we know in our prompt that it says that the liquid is filled through our distillation column. So for that, um, what we need to do, why am I going blank right now? Um, I think that's right, actually. Yeah, I think that's right. Yeah, 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 that's right. Okay, I'm not tweaking. That is correct. That is correct. Okay, and then for our condenser, yeah, that's right. Our L is just our reflux plus our distillation, our distillate. That's really all it is. Yes, that's what my songs. I was getting our condenser switched up with our liquid condenser. Our condenser comes from the liquid mixed up with our liquid initially. So then we can start with our condenser. We know that um our initial liquid is equal to our vapor coming in from our rectifying stage. Um, I'm missing a step, aren't I? Yes, I need to state our stages. Okay, so for our stages, so our stages, so mobile balance for stages. Because I said rectifying, but we don't have a V rectifying. So our rectifying stages really just are so that will be our vapor in between stage one and then two and R. Actually, yeah, from one to NR. So we know NR is three, so it'll be from one, two, three. We want to have it from one to three. So NR, but we want to have it stopped at four. So because if we put that into the brackets, when we have this four and put it, it won't actually count that value. So we need to do plus one. Okay. So then this will equal, okay, there we go. That will be equal to our V rectifying. Okay. Because it's, oh my gosh, what is that? V rectifying, so the vapor coming in from our rectifying stage. Um, yeah, that's pretty much it. And then, no, not that, but, and then, so that is VREC. I don't know why. Equal to our VREC. And then our vapor from the rest of our streams is really, so from NR on. So NR plus one to the rest of the distillation column would just be VREC. Um, um, plus, actually be minus our feed times the quality because we know the quality coming in liquids we need in the vapor form. So we 1 minus our Q. Yeah, oh my gosh. 1 minus our Q. Okay. I think it seems off. Yeah. Because when I'm gonna because I now have the stages, we can now get to our condenser. Um, but this doesn't seem right. I think it has to do with our flow rates. Yeah. Because I mean the mobiles, let me see. Because L is equal to R plus D. That's reflux times our distillate, which is correct. That is L initial. Um, so that's right. And then we know that our L initial is just equal to our VREC. But it says we don't have vector files, so that means I missed a step. So let me put this up here, because I think that's the reason why it's showing like that. Why? Because I was wondering why we have squiggly lines. What the heck? There we go. VREC. I'll be right back, because something's not making sense. Something's not adding up right now, and it's kind of throwing me off. Let me finish this off real quick. 1 minus Q for our quality, because now it has it in the liquid form. But I'll be right back. Something isn't seem right. Okay, so I came back. Yes, I knew something was off. I was getting everything switched up in order. So basically, we can just comment this out for now. Everything right now, we can just comment out. All this stuff can comment out. We can get back to our flow rates. So our vapor is correct. With our liquid, it's not correct. So what we need to put is actually MP dot rare, which actually, and I have it up here, so I don't know why I didn't get like a notification in my mind to like just come to this, but it helps us return the condition, a chosen condition for X or Y. So it basically kind of acts like an if statement in our array, which is kind of nice. So what we would actually want to have is because we need to state our liquid, because this is what I was trying to think of. Because like I said, we know that there's liquid currently in our distillation column, but it's currently below our threshold for our weir. So remember again, like our weir here, we need our liquid to be over our weir to have a hold up. Then once we have a hold, once it gets over the hold up, we can liquid actually start flowing down from the stage, but it has to reach a certain threshold. It has to reach certain height before it can even get over it. So we have to actually state that. So we have to say if M is less than our M hold up, then it'll be zero because there's no difference. Like it's below the difference we need. But then once our moles is higher than our moles of our hold up, then we have to input our weir equation, which is our weir times our moles minus our moles hold up. 2 3/2, 1.5. Okay. Okay. So now we have our moles for our flow rate. Now we can go to our condenser. Well, for our condenser, we can say that our condenser, the liquid leaving from our condenser, is the I'll bring for it again. The moles leaving is the VREC. So which is the vapor coming in from the rectifying stage. And VREC, oh my goodness, why does it keep doing that? It's from the rectifying stage. And VREC, the vapor from the rectifying stage, is just equal to our liquid coming from our condenser plus our distillate. Okay. And we know that because our condenser is a perfect controller. Okay. So since it's a perfect controller, we know that our liquid coming down plus our distillate is equal to our vapor coming in from our rectifying stage. That's why I kept trying to think. That's why I was like, I was saying it, but like it wasn't clicking. So now it makes sense. So now we can go, now we have our condenser. And now we can go to our stages. Okay. So from our stages, we can now state that these are just our VREC. This is our rectifying stage because this is just all vapor coming from rectifying stage. Then from our stripping stage, we have to also incorporate the feed. So from this, we have to subtract the feed from it because that's the liquid. So we have our rectifying vapor because remember all the vapor is coming from our reboiler. So it's the same rectifying, but we're subtracting it from our condenser as well. I mean, subtracting it from the feed that's currently coming in from our liquid. But if we know there is no liquid, I mean there was no vapor coming in from our feed because it's all liquid vapor stream. So that's there that's there. Because if we do change it, we can actually incorporate it into our distillation column later on. But for now, it's just that. So now we have that situated. I knew that something was off. we can now get into our derivations. So we can actually start our derivations. We can start actually putting these in. So for our mole balance, um, mole balance, we can start with our DM, and this would be from this would be from 1 to 6, so all the in-between equilibrium stages, including the feed as well. So from 1 all the way to our 6, and we'll be inputting this equation in right here. So this is the um change in mole flow rate in between our stages. So we will just have our liquid at at from our initial from 0 to -6, I mean to 6, position 6, because we have n-1, and this is the respective we started here. So this is right after our condenser. So this is where this is if we started right here. This is to respect to. Okay. Um, and then minus, that initial stage that we're at. So it's just 1 to -1. Um, oh no, should be a column. Oh my goodness. Excuse me. Then we do vapor, and vapor is n+1. So this would be SB 2 to the end of column to 0.7. So our vapor coming all the way, leaving from our stage all the way to our reboiler. Then minus our vapor of the stage. So 1 to -1. Okay. Next we will do our what? No, this needs to be here, and this is defining our vapor. Okay. So then a mole balance for our condenser. This is the easier one. This would just be, and we have this written down as well. It's this right here because we know it's equal to 0. DM at 0. This would just be equal to our vapor at the stage below, minus our liquid at condenser, then minus our distillate. Okay. And then our reboiler. This will just be our last stage, so -1. And then this should be, we have this here as well. So it'll be the liquid coming down from the stage above. So L -2 to represent stage 6. Minus the vapor at the reboiler. So a -1. And then the liquid, so our bottoms. We didn't have a defining variable, like a defining term for our bottoms, but we know that it's just a liquid leaving the bottom, so we can just put it as L at our reboiler. Okay. So then and then our last thing we need is our feed. And then our feed, we're just actually doing a accumulation. So we would just do NR. It's 3, NR is 3, and that's where our stages of our gets incorporated right after our rectifying. So NR, and we're actually doing an accumulation. So we do plus equal to, so we can keep adding on into our feed, and then it should be our F. So that means you're just adding on our feed into stage 3. Okay. And that's it. That's actually the most difficult part of the code, putting in our derivations. And then what we're gonna do here, we can actually copy and paste this, because if you remember, all of our mole fractions, are actually, we just have to add our components. So all we do is just we just do for liquids, we add our liquid mole fraction. So our X gonna be the same. Um, and it'll be the same thing inside the brackets for our mole fractions as well. So nothing really changes here. Just have to incorporate this, uh, then multiply them. And then for what, and then for our vapors, be our labor mole fractions, same thing. Okay. And then we can do this for this as well. So we have y two, one, I don't know why it's okay. And then x 0, and then we need to add a yes, x for our distillate, which I think is a z. We just add z here. Do we? I think we just put 0. I think we just actually just keep 0. Yeah, we keep 0. And then speed for our reboiler, -2, y, -1, and then our x for our liquid, -1. Yeah. All right. And then we just times z here. And then we have everything. So we have our mole balance for our mole flow rates and then for our mole fractions. And the last thing we need is we need our mole fraction by itself. Because this is our DMX. So we need to actually have dx by itself. We actually this as well. It's just this derivation. So what we would do, so we have dx, and we know this is equal to 1 divided by, actually, I'll just do that at the end, but we will have our DMX minus, and I'll put this in brackets because that's a lot. Our DMX, so all this, so we're taking DMX minus our X times our DM. Okay. And then divided by our M. And then this is all over 1. Okay. Actually, no, it's not over 1. That's it. Yeah. So this is the expression. Yeah. I was like, what? Yeah, this is the expression. All right. So this is dx. So now we have our mole fraction. Okay. And now all we need to do is return. I guess we'll return right. We'll put this into a array, into a row, and then we'll just return our change in moles and then our change in mole fractions. Shift enter. Hopefully that works. Let's go. Let's go. Okay, so next thing we'll do is we'll put this into a solver. So we'll do solve IVP, of course, and then so we'll start off with 10 is equal to 300, and then oh no, we'll do solve IVP, and then for our IVP, we'll do our function. So right hand side, next our time span. So we do from 0 to 10. Next, our y, our initial y guess. we know this is just NP dot R uh DM. So our moles and then our mole fractions. We have our method, which is redo. And then we have, what else we have? We have a dense output because it's a continuous function. Well, to an extent, because we do have a stop, but it's a continuous function. And then we have to say it's equal to true. That's what dense output, right? Dense output, yeah, I did. Okay. Um, pretty sure this is right. Yeah, let's see if this works. DM is not defined. Okay, we may have a problem. You may have a problem. Um, our initial guess. No, our initial guess is actually M0 X0. Yeah, duh. That's our initial guess. Yeah, our initial guess is M0. Why did I get that's our change. X0. Yes. So now we should be good. Missing requirement for our function. Hmm? It's no requirement because we have our argument. Yes, we need an argument. Because we have two functions, we need an argument. So we do lambda. Lambda, I think it's 2. Positional argument follows. Oh, I forgot it equals something. Come on, work. Invalid syntax. Is it not? It's a comma though. Is there not a comma? That's what I thought. It's a comma. For a lamp. Let me see argument. Arg, question mark. Okay, so the one time that didn't work. Okay, I swear this is supposed to work. It's supposed to be a comma after invalid syntax. That should be right though. I'm pretty sure this is right. I don't know what the problem is. Like legitimate. Let me see. Let me look this up. Um, argument, any, none. Oh, because it's args. Okay. There we go. There we go. There we go. We're good now. We're good now. I'll be right back. I don't know what's wrong. I'll be right back. Okay, so I checked. I don't know why I was thinking about this. So lambda, because the lambda is a function as we respect the time. So we had to do t, and that's oh no, no, no. Hold on. We had to do t for time in respect to that, and then put our for the two um um for our two vectors. So that's why it was not working. Also, when I went back, I also went to check on everything else, see everything was correct. Cause and there's a few things. One, our mode condenser for our mode balance for our condenser. I don't know why. I literally said it and I had it at first and I literally changed it because when I did my rechange for defining my volume, I mean my vapor flow rate, I actually put V rectifying again for the condenser, which is just, but it's literally just R plus R rectifying, I mean reflux plus R plus a distillate, which I had initially. I had it for the V rec, so that's the correct one now. Also I forgot to put multiple times for the finding our V. Um, so yeah, that's there now. That should be all the fixes. Um, I mean for our flow, sorry. The flow when you multiply for our quality. That should be correct now. So if I should enter this, this should be correct, and now this should work as well. And yeah, now we get our results. As you see, as time progresses over time, our mole fractions, I mean our moles decrease. Okay. Well, actually, they increase. Do they? Let me see. They increase. They should decrease. I'm pretty sure. Well, we'll see. I'm going to plot this out, and then if it, I'm pretty sure decrease is supposed to be decrease, not increase. Yeah, it should decrease. Hmm. I'm gonna just plot this out. I may be wrong. Because this has happened before. I was wrong. But I'll let me plot this out, see where I get, and then if there's a mistake, I will come back and try to fix it. Okay. So for plotting this out, we already defined our tend. Um, let me make this res. So we have a, oh, sorry, equal on my equal. There we go. All right. So apply this out. We need to start off with T plot again. NP list space. 0, 10, and then we do 100 points. And then we need to resplit out our vector for our moles and our mole fraction. So this be MS, and our XS. This be equal to NP dot split. This be for, we want the solutions this time. I mean the results this time. So be res dot solutions. And then respect to our time. Okay. Now let's plot this out. So we have big 2, because our second. Why is our my number lock keeps messing up? It's equal to make subplots. And then we want 2 columns, one for our moles and one for our mole fractions. So we do rows is equal to 1. And then our columns equal to 2. And then we'll do fig. Well, actually, we need a for loop for both of our 2 vectors. So for for ms, and for m and ms's. Fig 2 dot add scatter, and then x is equal to t plot, y is equal to m, rows equal to 1, columns equal to 1, and then the name is moles. And then we'll do the same thing for our mole frac. So x and x's, fig, actually I can just copy this. Okay. This should be x now. And then this would be column 2. And then rack. Okay. And then we also gonna take the update layout that we had down here. Copy, paste, and this be for fig 2. And then we do height. Let's say, 500. That's good. And we do width. Let's say 800. And then template poly. Please help this works. Okay. Huh? Oh, I forgot to put this. Got the two. The above shred cause the following exceptions. Huh? I've never seen this error before. Oh, okay. So this is not right at all. Yeah, that's what I thought. Yeah, it's supposed to be decreasing, not increasing. And now we just see why. Yeah, we're not supposed to have an increase of moles. The moles should decrease as we read. Our distillation column goes through. I will check what the problem is. Because probably it definitely has to do with our stages. Something probably messed up in between here. I'll be right back and I'll figure out what I messed up on. Okay, so I checked and it was two small things that were making this really like spaz out. One for our initial Y, and I'll go to it. I needed just to put brackets around the end because the way it was calculating it, it was going straight across, but we need to have this be contained so it can, calculate for it before it gets divided by the numerator. And then the other thing is for our condenser, it keeps coming down to our initial condenser set. It's actually it's our reflux times our distillate, not plus our distillate. So it's R times D. So once we have that stated, this is our function is now fully correct. And then this helps with our results. So now as you see our pretty sure, yeah, this is correct now. So our calculation, so our time, so also notice too in our results that our time was decreasing, which wasn't really making sense. It should be increasing over time. So I knew something had to do with our function. But now you see our time as our time increases, our moles decreases. So we see we start up here and then we get to we start at 5.25, I mean 2.1717, and then we go to 1.45 e to -1. So it decreases for the moles and for mole fractions. It did 5.25, -1 to 8.96. So we see a decrease, not increase over time, which is what we want. So now if we go to our plot, bam. So here is actually where we this is actually correct. Correct graphs for our mole flow rate and mole fraction. I can't believe we made it. But basically, if we start at the first one, um, what the heck? Why is it like this? Okay, I don't know why. I don't know why it looks like this, which is kind of strange because it looks. I mean, this is pretty much correct. I don't know why it does this. to begin with, like a mini heartbeat. But basically it should be somewhat straight. It should be the same. There should be no variance, but it doesn't really move. As you see, it stays at 2.7. Um, Even the time, I don't know why it's just a big, spike. But as you see, we go to our next value, our next mole, you see is relatively constant, which we want. So, and then we see over time, the moles in our distillation column, and then we get to our mole fraction. Normal fraction is steady decreases over time. So here is um our um the dynamic distillation. Yeah, I don't know why. It's late night. It's You can tell it's late. Yeah. Hope this helped you guys. I know it was a kind of a longer one, but we got it through. We got it done. And for our next part, I know it's kind of like the same thing what we're doing in McCabe-Thiele, a diagram as well. So that'll be the next part of our discussion column. So be ready for that. But yeah, I'll see you guys in the next video.